Hi everybody, this is Mrs. T and this is a review video for Redox. This is Mrs. T's Chem Talk Regions Chem. And so for those of you who don't know me, I'm Mrs. T. This is Tamanella. I'm a chemistry teacher from Calhoun High School in Merrick, New York. And hopefully this will be a nice review for the entire chapter for Redox for us. So the first thing we talked about in this chapter is assigning oxidation numbers. And in order to be able to assign oxidation numbers, you have to know where to find them. So if you notice on the periodic table, we have our little key here, and this is found at the top of the periodic table. And it says that for every element, a number of selected oxidation states are going to be found in this top right corner of the box on the periodic table. So these selected oxidation states are not necessarily an exhaustive list. There may be other possible oxidation numbers that are not listed here, but the very first thing that we're going to want to look at is this section for each element on the periodic table, because it will help us at least to give us a guide of what the possibilities are for the different elements that we're talking about. So the next thing is that we have some rules for assigning oxidation numbers. And for free elements, we assign those oxidation numbers as 0. So for example, if we have Br2, the oxidation number is a 0. Or if we just have Mg, the oxidation number is a 0. So the important part for this is that the element has to be written by itself and with no charge associated with it, and that would mean that its oxidation number is a 0. So simple ions are going to have their oxidation number given as the charge. So for example, if you have Na+, that would mean that +1 is the oxidation number. Or for example, if you had F-, that would mean that -1 is the oxidation number. So for these simple ions, what we're saying is that if a charge is already written, they're giving you the oxidation number. So if you look at the periodic table for group 1 elements, for example, are sodium or lithium. In a compound, their charge only can possibly be a +1. So for example, in NaCl, sodium's oxidation number is a +1, that's sodium in a compound, and chlorine's oxidation number is a -1. So on the periodic table, sodium is in group 1, so in a compound, its only choice is a +1. For group 2 elements, like maybe magnesium, the only choice in a compound is going to be +2. So for example, when we did magnesium chloride and we crisscrossed and dropped the signs, we were actually using the oxidation states. And when we crisscrossed and dropped the signs, we got MgCl2 because magnesium's oxidation number was a +2 and chloride's oxidation number was a -1. Remember that fluorine is the most electronegative element, so therefore it's always going to be negative. It's always going to be associated with having greater pull on the electrons in a compound. Its only oxidation number that's possible is -1. So for example, if we had sodium fluoride, sodium, which we learned is a group 1 element, has to be +1 in a compound. Fluorine has to be -1 in a compound. Aluminum and gallium only have a +3 as a choice in a compound. So for example, if aluminum is +3, the compound formula would be AlCl3 when we crisscross and drop the signs, because aluminum is +3 and chlorine is -1. If we had gallium fluoride, that would also be GaF3 because of the +3 and the -1. Hydrogen in most compounds is a +1. So for example, in HCl, hydrogen is a +1, chlorine is a -1. Hydrogen's one exception is in compounds that are called hydrides, so metal hydrides. So if you have a metal in front of hydrogen with no other elements present, this is when hydrogen is a -1. So NaH, or if you had CaH2, These are the two cases or two of the examples of where hydrogen is a negative one, but almost every compound, hydrogen is a positive one. And oxygen is usually a negative 2 in compounds. So for example, in H2O, hydrogen is a +1 and oxygen is a negative 2. And these are oxygen's exceptions here. In OF2, oxygen is a +2. In BaO2 and H2O2, oxygen is a -1. These are called peroxides. So OF2 and in peroxides are the times when oxygen is not a negative 2, but otherwise oxygen in a compound is going to have a negative 2 as its oxidation state. So now that we've done some of our rules, if we want to find these oxidation numbers, we're going to try to look at the periodic table to fill in as many choices that only, as many elements that only have one choice as possible. So for a compound, the sum of the oxidation numbers has to add up to 0. For ions, the sum of the oxidation numbers has to add up to, the charge. So for example, this is a compound, so these oxidation numbers are going to add up to 0. This is a compound, these oxidation numbers are going to add up to 0. But notice here we have a charge. That means that the oxidation numbers in this ion are going to add up to that given charge. So if we want to plug in as many as we can that only have one choice, this is hydrogen not in its exception, so it's a +1. Oxygen not in its exception, so it's a -2. We multiply on the way down to get the total charge. Any blanks, we leave blank. And we know that we have to put something in here that completes the expression. So that means that a +5 would complete the expression down here, divided by an understood subscript of 1, which means that phosphorus's oxidation number is a +5. So the oxidation numbers are +1 for hydrogen, +5 for phosphorus, -2 for oxygen, and down here, these are just our total charges and our work. Up here is where we put the oxidation numbers. So for the CaH2, we said this was an exception. This is a metal with just one symbol in front of an H. So this is where the hydrogen is its exception. And its exception, we said, was that when it's after a metal with nothing else, it's a -1. We multiply on the way down to get to -2. And some number has to go with -2 to get to 0, which means that calcium's oxidation state is +2. This is an element all by itself, oxidation number of 0. Even though there's a subscript, it's still just one symbol, one capital letter. Here, we plug in our -2 for the oxygen. The total has to be 0. Some number goes with -2 to get to 0, and it's going to be a +2. Here, group 1 element in a compound is a +1. It's the only choice on the periodic table. This is not one of oxygen's exceptions. It's not OF2, it's not BaO2, it's not H2O2, so we can plug in that automatic -2. Multiply on the way down. This is a blank. Has to add up to 0 because it's a compound. And the number that fills in the box, the box is a little too small. The number that is going to fill in the blank is a +5, which we divide on the way back up, and we get a +5. And we said for this one, it's going to be a little different because this whole thing has to add up to a -2. So we're going to plug in our -2 for our oxygen because this is not one of the exceptions. We multiply on the way down. -2 times 4 is a -8. Some number goes with a -8 and the total has to be a -2. That means that the sulfur here is a +6. So the next thing we're going to introduce is that GR is said by Leo. We're going to define that gaining electrons is reduction and the oxidation number will decrease or go down. Losing electrons is oxidation and the oxidation number will increase, because if we're gaining something negative, the charge becomes more negative. If we're losing something negative, the charge becomes more positive. So the first step is going to be to go in and plug in all of the oxidation numbers, which if you had trouble with finding the oxidation numbers, you should go back a little bit and go back over that. I then pull down just one element at a time to trace what happened to the oxidation numbers. And notice this is a Brinkelhoff. It's a diatomic, so it keeps its subscript. That means that on the other side we need to put a 2Cl. Notice I didn't put any arrows yet, but I put the left-hand charges on the left and the right-hand charges on the right. And what I can see is that the sodium's charge is increasing, so I'm going to call that Leo up. The chlorine's charge is decreasing, so I'm going to call that GR down. That means that sodium with a zero charge is being oxidized in this reaction and is losing electrons, and the chlorine with a zero charge is gaining electrons and is being reduced. So I'm just going to check something for a second. Yes, so we're going to go and see about half reactions and net ionic equations next. So if I go back in and I plug in my oxidation numbers, I have zeros for the elements that are by themselves. I have +1 for hydrogen in a compound, -2 for oxygen in a compound, +1 because sodium is a group 1 metal. And when I do the math for sulfate, the S always comes out to +6. So right now I'm introducing a spectator. This right here, the SO4, the sulfate ion, none of those charges have changed. So it's as if they're just watching the reaction and just not really taking part in the redox. So I'm going to pull down the species whose charges are changing. Remember, only keeping a subscript if this element is by itself in an element state. So H2, it's a diatomic, so it gets to keep its 2. That means that on the other side I need a 2H + 1, but sodium is not. It's there's no subscript here, and this is in a compound, so I don't keep that subscript here. So I'm going to label this one Leo up, and this one GR down, because the charge here is going from 0 up to +1. That means that sodium with a 0 charge is oxidized. Sodium with a 0 charge loses electrons. I'm going to label this one GR down because +1 that is what the charge starts at, and it goes down to 0. That means that H with a +1 is reduced. That means H with a +1 is gaining electrons in this reaction. So since we want to be able to trace the electrons, if something is lost, that means that it's written as a product, and 0 to +1 is a difference of 1 mole of electrons. So that would be a 1, or we could just leave it blank if we wanted to. For the H +1, I have to gain electrons, which means that the electrons have to be a reactant. Notice I drew the arrows in after I placed the electrons. And +1 down to 0 is a change of 1 mole of electrons, but I have a coefficient of 2. So that means that it has to happen twice. That means that I'm going to put 2 in front of my electrons. If you noticed before, we also said GR by Leo. The electrons for reduction go before the arrow. The electrons for oxidation go after the arrow. So reduction, electrons were before the arrow. Oxidation, electrons were after the arrow. So now these are my 2 half reactions. 1 half reaction for oxidation, that's our Leo. 1 half reaction for reduction, that's our GR. So we're going to label this one oxidation, this one reduction. But what I notice is that I don't have a total balance of charge. And the reason I don't have a total balance of charge is because I have 1 mole of electrons in my oxidation half reaction, 2 moles of electrons in my reduction half reaction. So what I'm going to do is multiply 1 or both of the half reactions by a coefficient that gets the electrons to be equal. So once I decide what that coefficient is going to be, I'm just going to put one single line through it, and I'm going to distribute it through and multiply all of the coefficients, all the numbers in front, by that number. And now when my electrons each have the same coefficient, now my half reactions are balanced. And the next thing I'm going to do is I'm going to combine the half reactions into one net ionic equation. I'm going to take all of my reactants, which are all of the things that happen before the arrow, and put them on one side, and all of my products, which are all of the species after the arrow, and put them on the other side. So I have 2Na0 plus 2H plus 1 plus 2 electrons yields 2Na plus 1 plus H20 plus 2 moles of electrons. And what I notice is that the 2E minus shows up on both sides. So I take it out of my net ionic equation. And what you can even do is actually cancel it out before you bring everything down. And now I have a net ionic equation that says 2Na0 plus 2H plus 1 yields 2Na plus 1 plus H20. I have 2 moles of Na on each side. I have 2 moles of H on each side. I have an equal charge on each side. I had the same number of electrons in the two half reactions, so my net ionic equation is balanced. So if we wanted to know whether a reaction for redox was going to be spontaneous, metals, if it's just a reaction between two metals, we want the more active metal from table J to be oxidized, because remember, the more active a metal is, the more easily it loses electrons, so that would mean that it would be oxidized more easily. And for a reaction between two nonmetals, like a single replacement reaction between nonmetals, we would want the more active nonmetal to be reduced. Because since nonmetals tend to gain electrons in a single replacement reaction between nonmetals, if the more active nonmetal is gaining electrons, it would be reduced. That would be more likely to happen. That would be for a spontaneous reaction. We have something called a voltaic cell, which a voltaic cell is something that uses a redox reaction to produce electricity. These would be spontaneous redox reactions, so they're ones where the more active metal is oxidized or the more active nonmetal is reduced. Batteries are examples of voltaic cells, and I like to use the memory tool active anode, which means you're going to look at table J, and the more active metal is going to act as the anode. I like to take the letter N in anode and remind me that the anode is going to be negative in a voltaic cell, and this is an example of a picture of a voltaic cell. Oops, I need to go back for a second. And for example, on this voltaic cell, we have a lead electrode and a silver electrode. And if we just go back for a second, oops, on a pen. If we just go back for a second, we can see that lead is here, silver is here. That would mean that in a voltaic cell, between lead and silver, lead would have to be the anode. And in this case, so Pb would be my active anode. And in this case, I have a Pb electrode and a silver electrode, and I can see that Pb goes from 0 to +2. So Pb is the oxidation reaction, and oxidation is what happens at the anode. I use the memory tool anox, and I also use the memory tool big red cat to remind me that reduction happens at the cathode. And if I notice, I have Ag plus going to Ag0, so that's the charge going down. So that's going to be, so I'm going to call this side the cathode. So the Ag electrode will be called the cathode because it's where reduction happens. The lead electrode will be called the anode because that's where oxidation happens. The wire is where electrons flow, and they flow from anode, where they're lost, to the cathode, where they're gained. And the salt bridge is for the flow of ions, and inside each half cell, we have a solution with the ions present. So what happens in this side, we are taking Pb, which is the actual anode, and losing electrons through the wire, making Pb plus 2 ions go into the solution. Here the Ag plus ions are joining with those electrons, right? Ag plus are joining with the electrons to make more silver, and so my cathode gets bigger because as the electrons travel there, the ions plate onto it. So this is actually able to be used as a battery. It generates electricity because the redox reaction is spontaneous and produces electricity. So in all of your batteries, you have a redox reaction happening. When we talk about an electrolytic cell, we're actually going to have electricity causing a redox reaction. So it's a non-spontaneous redox reaction. Recharging a battery is an example of this, and so is electroplating. This is an example of a simple electrolytic cell where we are recharging the battery, and in this case, it is the less active is the anode, because this isn't what would naturally happen. Just make sure, yeah. Since this isn't what would naturally happen, the less active is the anode to the positive. And what happens is that the battery, or the source of electricity, we're actually forcing the electrons instead of allowing them to go in their natural direction. So we're using electricity to push the electrons in the direction that they wouldn't normally go, and we're causing the reverse reaction to happen. Electrons still go through the wire, still goes from anode to cathode. Anode is still the site of oxidation. Reduction still happens at the cathode, but now we're just pushing the electrons in the direction that they wouldn't normally go. And electroplating is an application of electrolytic cells where we actually still use electricity to cause a non-spontaneous redox reaction, and we're usually causing one object to be plated onto another. So the key, or the object, is going to be the cathode, and it will be connected to the negative side of the battery. The anode will be the metal that we want to put on the outside so that it's still oxidized. We lose the electrons into the battery, and then the electrons go into the object, and the ions that leave the anode actually travel to meet the electrons on the side of the object. So the ions are going to travel through the solution, the electrons are going to travel through the wire, and we usually oxidize and then reduce the same metal. It's non-spontaneous, we have to provide electricity to cause it, and the cathode is usually the key, or the object. Could be a necklace, could be something else. So this was just a quick review of redox and electrochemistry. If you have any other questions, please feel free to see me in Extra Help if you're one of my students. If not, you can find some other review videos on YouTube for under Mrs. T Chem Talk. Okay, and I have some other review videos there. Hopefully you found this helpful, and have a good day.